Okay, welcome. My name is Ryan Hoger with Temperature Equipment Corporation, and this week's webinar, and actually the webinar for this week and next week, is Advanced RTU Control Strategies. ARC seems to be the trade name for that nowadays. It is going to be a two-part webinar. Each part is an hour and a half. For those of you interested in PDH credits, you will need to attend both halves to get the credits. For those of you just hanging out with us, well, then it's totally up to you. Normally we do 1 hour webinars, and when I started coming up to this topic, it was going to be about 3 hours after I cut a bunch of stuff out. So I really couldn't bring up myself to making it only 1 hour. So I'm leaving it at 3 hours and dividing it into 2 days for an hour and a half each day. For you guys that need PDH credits, you will have to make sure you pay attention and answer the poll questions. In the past, we also used the GoToMeeting attentiveness score to make sure you got credits that way. We're not going to do that this time because we've had some issues with that. So there's going to be a few more poll questions than normal. So you will have to make sure you answer all of those. And you will need to pass 70% of the questions. So many of them are not that hard. If you're paying attention, you should be in good shape. All right, let's go. All right, so some of you guys have seen this slide before. I won't spend a lot of time on it, just pointing out that depending on whose data you look at, buildings, both residential and commercial combined, use 28 to 40% of all of the energy of the entire country. That's all energy, right? So we're looking at industrial, manufacturing, planes, trains, and automobiles, buildings, etc. So basically a third of the energy is going towards building use. And when you look at that and look at the pie chart there, half of that, really, almost half of that, is related to HVAC. So we have a pretty big effect on the energy's total energy consumption for the entire country. What I want to do, though, is look at it in pieces here, if you will. So on the left side of the screen, and some of you guys may have seen this particular chart before, the left side of the screen, you'll see cooling energy for the country. And this data is a little bit old. It's 10-year-old data now. But we're using 1.4 quads of energy for cooling systems. And half of that, or 54% on this chart, was related to packaged rooftop units. And then the other wedges there, 3 or 4 of those wedges are different types of chillers. And then you got some of your individual zoned units like PTACs, heat pumps, racks, etc. But more than half of it, packaged rooftop units. So it is a huge part of the market that's kind of sort of been neglected from the energy standpoint for decades. On the right-hand side is the heating energy, 1.7 quads of energy for the country, so a little more energy used to heat than cool on commercial buildings on average. And a quarter of that is packaged rooftop units, a quarter of its furnaces, a quarter of its boilers, a quarter of its unit heaters. Right? So we can still affect a lot of energy on the heating side, not just the cooling side. But the interesting part is what we call the parasitic energy, or the transportation energy. So we're making cooling, we're making heating, but how much money does it cost, or how much energy does it cost to move all this heating and cooling around the building? So you look at the bottom chart there, it's 1.5 quads of energy for transportation costs, fans and pumps basically. We spend more energy on fans and pumps than we actually do on the cooling cycles themselves. And we look at that, half of that is the supply return duct system. So literally half of the fan energy is used on rooftop units getting heating and cooling to the right spot. So we're going to pick on the fans a lot, not just today, but as a country in terms of energy codes, we're picking on the fans a lot because we've made the cooling systems pretty efficient, relatively speaking. So the fan guys are getting picked on next. So if you're a fan guy, I apologize. All right, so 27% of all the commercial HVAC energy is fan energy, right? And that's what we're really going to focus on a lot today. We're going to talk about lots of stuff today and next week, but fan energy is going to be one of those things. From a code standpoint, you've probably seen this chart before as well. Ashrae Standard 90 has been sort of our de facto energy code for a long time. In the 1970s, the federal government asked Ashrae to make an energy standard, and that's kind of what we came up with. And we used to update it infrequently every, 6, 7, 10 years or whatever. But now, as you can see, we're on a 3-year update cycle. Every 3 years, we update. Thanks, Dan. That's really helpful. We update every 3 years for the energy code. So we're currently on the 2012 energy code in most states. A few states, 2 specific states, have already adopted the 2015 energy code, which just came out. And then after that, it'll be 2018, 2021, and so on. Both Ashrae and the International Code both update every 3 years. The International Code updates about 18 months after the Ashrae Standards update. And that's basically, for lack of a better description, the code guys cut and paste the Ashrae stuff and put it into their book. They tweak a few things here and there or stuff that's not necessarily cost effective yet, but they basically cut and paste the tables out of the Ashrae and put them into the international code, which is what the states adopt. This is the adoption by state, so you can kind of see where you're at. For today's purposes, I'm going to be focusing on the Midwest and very much so on Illinois, because 85% of people that register for this webinar are from Illinois and 99% are from the Midwest. So I'm going to be focusing on the Midwest. So you can see the states in blue are the ones that are on the 2012 energy code. And Minnesota is highlighted in blue, but there's an asterisk. They've adopted it, but it hasn't gone live yet. I think it went live 2 months ago for residential, and I think commercial goes live soon. But in any case, from the purpose of designing a building, they're basically on the 2012 code from a design standpoint. So Illinois, Iowa, and Minnesota are in 2012. Wisconsin, Michigan, Indiana, Ohio, those are on the 2009 energy code, or Ashrae 90.1 2007, which is functionally the equivalent of the 2009 code. All right, and you can see the states in white don't have any codes, they don't give a crap, and then the states in green are the two that are ahead of the curve and have the very newest code out there. So let's start with the rooftops themselves, and then we'll work our way into all the widgets and gadgets that we can add on to them to make them even better. So rooftops, they're rated by AHRI like almost all HVAC equipment is. If you want to see the ratings for any equipment, HVAC-wise, if you go to ahridirectory.org, if you go to that website, you can search for anything you want. Chillers, small chillers, boilers, rooftop units, water heaters, furnaces, residential splits, everything, residential and commercial, are on there. For today's purposes, we're talking about packaged cooling equipment, which includes rooftop units. So rooftops get rated one of two ways depending on the size of the rooftop unit. It's very similar for split systems. So if something is smaller than 65,000 BTUs of cooling, which is a little more than 5 tons, then it gets rated under the residential standards. Those testing standards for cooling are SEER, Seasonal Energy Efficiency Ratio, and for heating, AFUE, Annual Fuel Utilization Efficiency. Right, those are the two terms that we use, same exact stuff we use for residential. We do that on the small package rooftops, irregardless of where you decide later to install this rooftop, in someone's yard at their house or on a roof at their commercial building. Those are the test standards. The quote-unquote big rooftops, the large package rooftops, so the stuff that's greater than 65,000 BTUs of cooling, get rated for cooling purposes with two different tests. There's EER, Energy Efficiency Ratio. What that basically means is run this unit at max capacity with 95-degree outdoor temperature and 80-degree return temperature with 67 wet bulb return. So running it at 95 and 80-67, max out, steady state condition. How much power did you use versus how much cooling power did you get out of the thing, right? That's what that EER is, and we've used that for decades. More recently, in the past several years, well, let me just say too, SEER, the residential version, is kind of like that, but it takes into account cycling losses and some part load type things. So the test is a little bit different on the residential side. You cannot compare EER to SER. There's no conversion factor. It cannot be done, right? You can make estimates and guesstimates on what might have happened, but it's a different testing pattern. So IEER, Integrated Energy Efficiency Ratio, is just like the EER, but it takes into account the fact, well, how often is it really 100% load scenario, 95 degrees outside with 80-67 return fully loaded? That hardly ever happens. So EER is kind of outdated and not really relevant. So now we use IEER. Basically what that does is we test it at 4 different points: 100% capacity, 75, 50, and 25%. So we tested these 4 different points. We got these 4 buckets of tests that we do. And the 2 middle ones, the 50 and 75, are heavily weighted. And the 25 and 100% operating point are very lowly weighted. Only a few percent of the hours of the test go into that bucket. So basically saying how efficient are you at these mid-tier ranges, because that's where you're going to spend most of your operating life. On the heating side, we rate it with thermal efficiency. This is basically how much, this is for gas units, how much natural gas did I buy, which quantity of gas did I buy versus what quantity of heat went into the duct system, right? That's really what that's telling me there. It's different than combustion efficiency, which looks at the exhaust stack temps, and it's way different than AFUE on the small stuff, because the AFUE, very much like SEER, takes into account cycling losses and things like that. So we can't really look at those. Right, so that's our rating points there. All right, so with that in mind, IER is a big deal. DOE, Department of Energy, has been looking at that as well. It's an important factor. And recently a challenge came out a couple years ago by the DOE to the rooftop manufacturers to rate these systems, to develop systems that could do very well in an IER test. And there was kind of bonuses and spiffs for doing that. And there was no EER requirement at all, only IER. You're going to see anything related to the Department of Energy going forward, anything related to the codes going forward, and we'll talk about that in a little bit. They're all focused on IER. Part load efficiency is not important anymore. Right? Hold on one second. I need to check something else. All right, looks like it is working. If anybody else is having any issue on sound, just send me a note and I'll try to answer your question there. But it looks like most folks are okay. All right, so the goal there was to make a 10-ton rooftop that's 18 IEER, and several manufacturers did meet that challenge. And these are now actually commercially available, and you can purchase these units and install them in your building if you wish. So kind of keeping on that theme, this is out of the Ashrae handbook. So if you're with the Ashrae police and you have copyright issues, then you can come yell at me. But I'm just looking at one little snapshot here. Looking at some weather conditions for areas near me. And I'm going to take the Chicago O'Hare Airport because that's very central to most people on the webinar. And if I go across the chart here and I look at things, I got my 0.4, my 1, and my 2% columns, depending on how stringent I want to be in my design day. If I look at the most strict, the 0.4% of the time column, my design dry bulb temperature outdoors is only 91 degrees. Right? So rooftops for EER are rated at 95. So even on design day in Chicago, let alone any other Midwestern state, right? 95 doesn't really, it's not really a concern to us. 91 is the main thing. I get that it could happen and every once in a while it does, but from a design standpoint, we should be designing for 91 or less outdoor temperature. On the heating side, by the way, as a point of reference for O'Hare, it's minus 1.5. And as you get closer to the city, it gets a little more mild. All right, so those are design days. Those don't happen very much. And when you look at all the hours and you lump them into buckets to see where the time falls, let me see if I can get my little pen thing working here. Right, so if I look at what I would call cooling days for a commercial building, and for me, cooling days is pretty much anything above 60, if you will. That's all these hours right here that I just circled. But how many of them are at 95? Or even in the 90 to 95 bucket? It's like less than 50 hours a year. It's very, very minor. Right? The bulk of the hours are in the 65, 70, 75, 80 degree type range. So that's where I'm really concerned with my efficiency, and that's where I really should be paying attention. All right, let me go back to my mouse. And by the way, these charts right here, right? These are for Illinois, for Chicago area. In my presentation, I have all the other Midwestern cities in here too. So if you need one of these charts for your city, just let me know. I just didn't have the time to go through every single city in the Midwest today, so I just picked the one where most people are from. But if you need one from Milwaukee or Duluth or whatever it is, let me know. So from an energy code standpoint, the majority of the states, as we said, are in the IEC 2012, which is the same as Ashrae 90.1 2010. And this is what is currently required by code in these types of states. Right? So this is what you have to do at an absolute bare minimum. So if I look at a 10-ton unit, which is 120,000 BTUs, right? I'm over in this range over here. What do I have to do from an efficiency standpoint? Let's assume I have a gas-fired rooftop because that's the majority of the market. So what do I have to do? I have to have 11.0 EER at a minimum and 11.2 IEER. That's what I got to do at a minimal absolute low end. Now, let me just point out one thing here. Every once in a while, I'll get somebody send me a table like this from the code book and say, no, Ryan, you said it had to be 11 and 11.2, but the code really says it's 11.4 and 11 point whatever. When that happens, it's because you're looking at the wrong table in the book. Sounds a little crude, but that's what you're doing. There's a table way in the back of the book for additional efficiency options, and it looks very similar to this table, but it's only if you are in that bucket. Most buildings take lighting as their additional efficiency option, so you don't have to do it for HVAC. And this becomes your minimum that I'm showing on the screen here. So just as a point of reference, you might be looking at the wrong table because they look exactly the same except for the numbers. Coming down the pipe, the next version, 90.1 2013, which usually kind of gives you a hint at what's going to happen with codes in the next 3 to 6 years. Right, if I look at that same scenario, right, 11 and 11.2, At a future date, Ashrae says for 2016, a year from now, you got to bump up the part load to 12.7. But they don't change the full load. Basically, Ashrae, much like the DOEs, decided full load doesn't matter. I don't care about full load. What can you do for me at part load? So the code will change for part load. The full load will stay the same. This is assuming that all the codes adopt Ashrae, which almost always does happen, but it's not, 100% lock type thing. So this is what you can expect for the future. Improvements on the refrigeration side to part load efficiencies, while pretty much we're maxed out on full load efficiency without getting ridiculously large equipment. If anybody has any questions as we go, type them in the question/chat box there, and I will do my best to try to answer those as they come up. I'm going to go check them right now, see if anything is on there at the moment. All right. All right, we're also going to go ahead and launch our first poll question for you guys here too, so we can stay on track with that. I'm going to put that up right now. The question is, true or false? More commercial buildings use packaged rooftop HVAC than any other type of cooling system. And while you guys are answering that, I'm going to go look and see if you have any questions that I need to answer for you so far. Looks like all the questions are good. Nothing I have to answer there. All right, 81% of the people voted. We'll give it another few seconds. I remember, if you need PDHs, you need to answer these questions. If you don't, then that's fine. All right, 90% of you voted, so I'm going to close it in 5, 4, 3, 2, 1. All right. Here's the results. Most of you got that correct. 96% of you said that is true. That was one of the easier questions. There'll be a few hard ones in here and a few easy ones, but you guys should be fine overall. All right, so back to our slides here. All right, so up on the screen, you're going to see a typical manufacturer's product offering. When we go below 25 tons, most manufacturers have 3 tiers of equipment. That just seems to be the way they do it. If you want to call it the good, better, best scenario, or the standard mid-tier and high-tier, whatever you want to call it. But most of them seem to have 3 offerings below 25 tons. When you get to the bigger sizes, they don't have as many because there's just not the volume there, so it's hard to support multiple lines. But on the low stuff, there is. Little stuff, there is. So for this chart, for right now, just ignore the blue stuff, which is SEER. That's the quote-unquote residential size units, which are 5 tons and under. So we don't really need to talk about that for the moment. Let's just talk about the big stuff, which is 6 tons and up. You got the 2 ratings there. The whatever that is, peach colored is the EER, and the green colored is the part load IEER, right? So if you look at the minimum code efficient rooftop all the way to the right hand side, he's at what, basically an 11 EER and 11.5 IER is the code minimum. And obviously it's different for different size units, but this is kind of a lumped in average, if you will. If I go to the mid efficiency unit, I can pick up basically a point on the EER and maybe a 1.5 on the IER, which is nice and it may be worth paying the extra money to upgrade and do that. And if I go to the the ultra efficient unit, I can probably pick up another 1.5 points, another point on EER, but I can get really, really good on the part load efficiency. And if you look up on top, I put some notes on there why that particular high tier unit does really rock star job at part load efficiency. It's because it has lots of stages of cooling. So instead of 1 or even 2 stages, it's a 3-stage unit. It's got a VFD on the supply fan, and it's got a variable speed condenser fan as well. So once again, kind of picking on the fan guys is kind of where we get there. Dan asks about the price. He says price penalty between units. That's a good question. There's a pretty dramatic difference, and we're going to save a little bit of that for next week when we talk about payback discussions on some of these things. So I'm going to table you for a little bit, Daniel. But I'll just say that going from the code minimum to the mid-tier is usually a nominal price difference, right? And I'll just make up a number right now, but on a 10-ton unit, it's a few $100. When I want to go to the ultimate high-tier efficiency, it's usually a pretty big price jump. And not even just because I'm putting the VFD and ECM on there. I have a different refrigerant circuit. Those things all add to it. But I'm also going to get a lot of non-energy features that come along for the ride, right? Because it's the high-tier unit. It's not the only the high-efficiency unit, right? So I'm going to get all kinds of extra digital controls on there. I'm going to get slide-out fan chassis, hinged access doors. I'm going to get all kinds of, quote unquote, sexy features, if you want to call HVAC sexy, that don't really affect my energy or my payback. They're just nice things to have. So we will talk about paybacks, though, next week. We'll get to that, Daniel. Thanks for the question. All right, so let's talk about some of the existing rooftops in the market. I'm going to reference 2 or 3 different studies that have pretty good detail on some of these things, just to kind of scare you, to let you know how crappy the market scenario really is. So this is a study that I like to use a lot, not just for rooftops, but for other stuff as well. It is about 5 years old now. It's a DOE study out of Lawrence Berkeley. On the left-hand side are most frequently implemented improvements on systems for retro-commissioning projects that they did. On the right-hand side were the ones that saved the most money per square foot. But some of these things directly relate to what we're going to do with rooftops frequently. For example, the most frequent retro-commissioning they did was to fix the air side economizer, or they call it optimize the air side economizer. I'm going to call it fix because so many are bad that I couldn't even call it optimized. That was even more common than reducing equipment runtime. And pretty much everybody who does retro-commissioning knows one of the main things you do is try to get all this crap on a schedule in a building that was supposed to have, right? The building's not occupied 24/7. Let's get the schedules fixed, and that solves a lot of problems. Well, fixing the economizer was even more frequently done in these studies than fixing the scheduling. Other stuff that came up that do relate to rooftop units, duct static pressure set point, when we got VAV rooftop units, optimizing the start-stop algorithm, and adding a VFD to the fan, the supply fan. Another way to sort of look at that are which ones save me the most energy. Fixing the control sequences on buildings, not just rooftops, but in general, was the biggest savings. Optimizing the runtime was the next one, and then the third one was optimizing the air side economizer. We could do all 3 of these things on packaged rooftop units. So there's quite a bit of savings to be had, just thinking about it that way. This study, though, I've been referencing for quite a long time. It's 10 years old now, which I realize is dated, but nobody's got a better what sucks with my rooftop study since then. So I still like this study. So this was basically going out to 180 some different buildings with like 500 rooftops from like 5 different manufacturers and figuring out what stuff doesn't work on the rooftops today in the field. Now, most of these buildings were out in the Pacific Northwest area, but I imagine all the same logic holds true in the Midwest and anywhere else. So 64% of the time, the economizer was not working. For you guys that are math whizzes, that's more than half of the time, right? And not working usually meant that it was broken, but it could have also been that it had just really screwed up settings that allowed it to barely operate. So problems that were incurred would be things like somebody propped open the damper with a 2x4. I know that's shocking to most of you, but people do that frequently. Somebody screwed the economizer damper shut so it would never open again. That also happens fairly frequently. The actuator is not on the damper shaft. It's laying on the ground. Why is it not on the shaft, right? And then to the less dramatic things like my economizer set point is not the optimal set point. Somebody set it to only change over at 45 degrees, right, instead of something more conservative that we'll talk about in a minute. So that was the most common. Thermostats, 58% of the time, were not optimized correctly. That doesn't necessarily mean they were failed, but it could mean that no one had a schedule in there whatsoever, at all, or they had set points that were not very useful, or they had a schedule with no set points, or they had heating and cooling running simultaneously, just a collection of things like that. But most of the time, it was not being scheduled. And then, lucky for us, only half the time, 46% of the time, was the refrigeration charge wrong, and only 42% of the time was the airflow wrong. So those sound really good. And then the controls guys that put all the little sensors on the unit, they only did a bad job 27% of the time, right? I'm picking on the controls guys because I used to be one, or I still am if you want to think of it that way. But we like to blame the sensors, but really there's a lot of stuff going wrong, but it's not really the sensor's fault. Right? So there's lots of things going wrong, so just fixing an existing unit can have a pretty substantial payback. So we're going to talk about today and next week about upgrading things on a unit to make them better and more efficient, but just getting stuff working the way it was supposed to work is really a pretty big payback in and of itself. So we do recommend when we talk to building owners that they have their rooftop tuned up twice a year, right? Once going into the cooling season, once going into the heating season. Most of them don't do it at all. And the ones that do regular scheduled maintenance typically do it going into the cooling season, and then they cross their fingers for the heating season. Just seems to be the way it is. This chart I'm showing here on the screen is just a typical chart of things we recommend that they do. This particular chart came out of the Wisconsin Focus on Energy Rooftop Tune-Up Program. But it's the same stuff that we recommend to just about anybody doing rooftop work, right? It's basically clean and inspect everything, right? Look at all the coils, look at the drain, look at the belts, that sort of thing. Check the filters, change them, etc. And then we want them to get some data, some measurements on compressor amp draw, blower motor amp draw, pressure drop across the evaporator coil, pressure drop across the heat exchanger if it's a gas furnace type thing. And then we want them to actually clean stuff, right? Clean the condenser, clean the evaporator coil. Why does that save energy? Well, dirt acts like an insulator. So if I have dirt on my coils, I'm reducing the heat transfer, which means my compression has to run longer in order to transfer heat, right? So I want clean evaporators and clean condenser coils in order to optimize my energy and optimize my BTU capacities. So that's the kind of stuff that we're typically asking for. Sometimes they need to put gauges on the refrigerant circuit if the temperatures are out of line. Sometimes you don't. If all the temperatures are in order, you don't really need to tap into the refrigeration circuit. So it just kind of depends on that. This is a typical chart, and there's a bunch of them out there like that. This is just one that I grabbed to show you. So getting things working the way they're supposed to work is step one. What we're going to talk about beyond that is, well, assuming they're all working correctly, what else can I do to save energy? I'm going to go ahead and launch a second quiz question. Well, we step into the next topic here. So the question here is, large rooftop units above, greater than 5 tons are rated with the following metrics. Right? So A, SEER and AFUE, B, EER and AFUE, C, EER, IER and thermal efficiency, D, EER, IER and AFUE. Right, so this is the big rooftops, 65,000 BTUs and up, 5.4 tons and larger. All right, so about 80% of the people voted. I'm going to give it another 10-15 seconds here. And I'll close it in 5, 4, 3, 2. All right, so I'm popping the answers up there for you. 65% of the people were correct in choosing C, which is EER, full load cooling, IEER, part load cooling, and thermal efficiency, that's the heating efficiency. Some people incorrectly guessed AFUE instead of thermal efficiency. AFUE is only for 65,000 cooling BTUs and under. All right, so back to our slides. I want to talk about one more study that came up recently because it's been really the driving force behind what we're going to do with some of the things we're going to talk about for the next session and a half here. A year and a half ago, a study came out of, once again, DOE, Pacific Northwest Labs, and this one was specifically for retrofitting advanced rooftop controls, right? That's why it really relates to what we're talking about today. So the things that they retrofitted on the rooftops in this study were economizers, which we'll talk about today, DCV, which we'll talk about today, and multi-speed fan control, which we'll definitely talk about today. There was a lot of analysis done on numerous units, but then they followed up the engineering study analysis with field testing as well on 66 units at 8 different buildings, various occupancy types, various climates, various manufacturers of units, in order to try to get a good representation of the things they were modeling to make sure that their models lined up with what their actual studies showed. And the majority of the rooftops in the study were in the 10 to 15 ton range, which is sort of the sweet spots for some of these technologies. Because you put some of these things on smaller units, the payback might not be there. And you put them on bigger units, well, they may have already had them on the bigger units because of code reasons anyway. So this is kind of like the sweet spot, although it does apply to bigger and smaller units. One of the cool things about this study, if you like data, which I do, is they collected data every minute for 12 months. That's a lot of flipping data, right? But technology is such you can do that these days. But the really cool thing is that most studies, they take some base case and they study that, and then they take some test buildings and they study those and make all the improvements over there, and they try to compare the base buildings to the test buildings, right? The problem is, well, the problem is people. There's different people in these buildings touching and messing with different things, right? So it doesn't really make a lot of sense. This particular study, the base building and the test building were the same building, and not even a before and after snapshot, simultaneous, meaning that today we're the base building, tomorrow we change out the controls and make them the test building. And then the day after that, we go back to being a base building and then a test building. Every other day, they rotated the control sequence between standard rooftop control sequence and advanced rooftop control sequence, the stuff we're going to talk about today. So it kind of eliminates the fact that somebody's propping open doors and windows and jerry-rigging thermostats and whatever else people do to get comfortable. Right, so that's kind of the nice thing about that. The study's findings, and by the way, I don't read 300-page studies. I read the executive summary, right? So that's kind of what I'm showing you here, because 300 pages it's not very exciting. If you're bored one day, you can read it. Overall, though, for the 66 rooftops, the savings range was 22 to 90%. So you can see on some units the savings can be absolutely massive, but even on the good buildings, there's still a 22% savings by doing some of this stuff. And on average, overall, for all 66 rooftops, 57% energy savings. All right. Some of the savings can get a little bit larger on heat pump systems than on gas systems, but still, if I get 25 to 35 to 40% savings on a gas rooftop, I'm a pretty happy camper. Of all these technologies that they did, which were mainly economizers, DCV, and fan savings was by far the dominant contributor of all the savings, right? And we already know economizers save a boatload of energy, and most of you guys have been hearing the DCV pitch for the past 10, 15 years, probably from me. And we know that saves a lot of energy. The fan energy savings by doing the staged air volume fans just totally rock starred it and crushed those other ones. So the dominant savings comes from fans, as you would expect. The paybacks really depend on the utility costs and utility rebates, right? So the higher utility cost, the faster the payback. Well, that's not surprising, obviously. And then the lower utility rates, the lower your payback. So if you have a 10-cent kilowatt-hour electric rebate like we have in many of the areas here in the Midwest, you're talking about a 3-year payback. If your rate's a little bit higher, you're more towards the 15-cent range, could be a 2-year payback for retrofitting some of these technologies. And then obviously if you have really cheap electricity, then the paybacks can be much longer. The payback costs include both the equipment costs, so dampers, VFDs, sensors, control widgets, etc., and the labor to install those things. These are all retrofits in this particular study. Not only the ones with the higher utility costs having good paybacks, but larger rooftops have shorter paybacks than smaller rooftops, right? The more CFM I'm running through the unit, the faster my savings could be. The control widgets basically cost the same whether I put them on a 5-ton unit or a 50-ton unit. Sure, the VFD gets a little larger, but the sensors and all that stuff, actuators, it's all the same. Right? So the bigger the unit, the faster the payback's going to be, right? Additionally, the ones with longer run times have faster paybacks, as you might expect. If you run something for 1 hour a week because you're at church, it's going to take a really long time to pay that back, right? But if you're occupied 12 hours a day for 5 days a week, payback's going to be a little bit quicker. In that particular study, they on paper, they analyzed 3 different manufacturers of retrofit packages. Obviously, anybody that builds control systems can do this stuff, but these guys make package stuff, package solutions that you call up and order, a kit in a box. They analyzed those 3, and they decided to use the Catalyst product because that, at the time, was the most advanced product that was ready to go to market and be installed on 66 units in the next week. But all 3 of these guys do kind of the same thing. They retrofit supply fans with VFDs. They change the speed based on the mode, and we're going to talk about that a lot next week, as opposed to static pressure. They change the speed based on the mode that you're in. They all have an integrated economizer sequence, which we're going to talk about today, and they all have demand-controlled ventilation, which we're going to talk about. One of them also does compressor modulation, which we'll talk about next week, but that was not part of this particular study from DOE. Like I said, they chose you the Catalyst product because it was the most mature product in the market at the time. So the way this test was set up is that they established 3 different speeds to use, right? So the first one was whenever you're in vent mode, meaning I don't want heating, I don't want cooling. The only reason I'm running this fan right now is because I need fresh air by code. If you're in that mode, run the fan at 40% of the airflow, right, from supply airflow. Obviously, you got to open up your Economizer Damper more. We'll talk about that too. If I want one stage of heating or cooling, run the fan at 75%. Now, you can argue 75%. In many cases, you can go a lot lower than that. But as just a safe number for them to pick, that's what they did. I suppose they could have done a study on each individual product at the sites and perhaps went down into the 60s or even 50% airflow range. But if I'm on one stage of heating and cooling, run 75%. If I want 2 stages of heating and cooling, the maximum, then run at 90%. you'll notice that they never ran at 100% at all, because in nearly 100% of the buildings across the entire country, all fans are oversized. Just like all cooling systems are oversized, and all boilers and all furnaces and everything else that all of us have ever done in our entire careers, we're all oversized. So they didn't even bother going to 100% airflow. They just went to 90, right? And that was sufficient for what they were trying to do. They had a CO2 set point of 1,000 parts per million, which is kind of conservative. They could certainly get more aggressive than that, and we'll talk about that today. But that's what they chose for this particular study. So this was kind of the summary, if you will. And like I said, there's a 300-page study. You can read it all. Jeff, by the way, types in and asks if the 8 buildings were in varying zones or just one zone. I'm not sure exactly what you mean by zones, but if you're asking if there were zoning systems on the rooftop units, no, there was no dampered zoning systems. If you're asking if they were on different zone exposures of a building, yes, different exposures. All right, so this was kind of the summary slide, and as you can see, like I said, the bigger the rooftop, the faster the payback, the more run hours, the faster the payback, the higher the utility rate, the faster the payback. The better their utility rate rebate incentives, the faster the payback, right? And you can come up with any number of combinations of those kinds of things. But for example, if I take a 10-ton unit that runs a typical 14 hours a day, right? So that's 7.5 to 12.5 tons, greater than 14 hours a day, with a 15-cent electric cost, I don't even need a utility rebate to make this make sense. And by the way, make sense is defined here as being a faster than 3-year payback, right? But if I have that same unit and I run less hours a day, less than 10, which is very small for an office building, with that same utility rebate of 15 cents, I need the utility to pick up half the tab, or it's not going to pay back in under 3 years, right? Oh, Jeff clarified his zoning question. Regional zones within the country. Yes, different climate zones represented in that particular study. By the way, if anybody wants the study, you can just send me an email and I will send you either a link to it or the actual file, depending on how big the file was. I don't remember. All right, this is my favorite slide out of that particular study because it's visual and I'm a visual person, right? So what this is showing you here, and this is not all the rooftops in that study. This is just 1, 2, 3, 4, 5, 6, 7, 8 of the rooftop units. In red, it shows the amount of runtime that was in the heating mode. And this is different climates, right? This is just a general statement. Baby blue is the ventilation mode. Green is economizer mode. Dark blue is mechanical cooling, and purple is integrated economizer mode, which we're going to talk about today, but that means the economizer and the compressor run in conjunction with each other. You can see, just visually looking at this, the dominant mode is obviously the ventilation mode for all these different building types, and this is not just for this study, this is everything you look at. Ventilation mode has the highest number of run hours of all packaged rooftop units. And then, relatively speaking, we very seldom kick on the compressor, turn on the gas burner, or open up the economizer damper. Sure, we're doing it for thousands of hours a year, but relative to the ventilation mode, it's nothing. Ventilation mode is the dominant mode, which is why when we start talking about things that save energy, like improving the refrigeration system, or if we somehow started installing 95% gas efficient rooftop units, that would be great, and we'd all love it. But compared to ventilation hours, it's kind of irrelevant. So there's a lot of ventilation hours, which is basically fan energy. So you can see why picking on the fans has the biggest payback scenario of all these things that we're going to discuss. All right, so we're going to start talking about different technologies now, and some of them we'll spend a short amount of time on them, such as programmable thermostats, because most of you guys get that. We'll just spend 5 minutes on that. But other things we'll spend a lot more time on, depending on what it is. So programmable thermostats. Obviously, the goal is stop running things 24/7. You would be shocked, maybe you wouldn't, but you'd be shocked at how many things are running 24/7 right now. Let me go back 1 second just while we're on it. Steve types in to ask if I can define economizer mode versus ventilation mode. Economizer mode means that I would like to use cool outdoor air to free cool my building. And we're going to discuss that in detail today. But let's say for argument's sake, it's 50 degrees outside and I need cooling in my building. I'm going to open up the economizer damper to get me that free cooling. Ventilation mode means that I have a damper that brings in fresh air to my building for ventilation, IAQ type code. I have to bring that fresh air in, unrelated to what the temperatures are outside or what I want inside. It doesn't make a difference, right? So we only have one damper on a rooftop unit. He's going to open to some ventilation position. For right now, let's say it's open at 20%. And he opens to that position and runs 20% outside air all day long, no matter what. Then, if he wants to go into economizer mode, meaning free cooling mode because it's nice outside and I don't want to run my compressor, then I modulate the damper more from 20% to something higher during that cooling cycle. So hopefully that clarifies it, Steve, and if not, when we talk about economizers in a little bit, it might help it a little bit more. So programmable thermostat, stop running 24/7. What a programmable stat does is basically relax the set points. In order to have things make some decent amount of sense from energy savings in a commercial building, I generally say you got to set back about 5 degrees. Sometimes you can get more aggressive than that and set it back 10 or 12 or 15 degrees. Two things happen though. One, when you come out of setback, it usually forces you to go into more stages of heating and cooling capacity, which is not necessarily the most efficient way to run your unit, so we don't always want to do that. And the other thing that happens is that all the surface temperatures in your building are, let's say in the wintertime, they're all really cold, and if I set back a lot, yeah, I recover and I heat up the air, but my surfaces are still cold for a while. So I don't like to get too aggressive with the setback. My rule of thumb is basically 5 degrees. Normally I set a building up for 70 degrees heating, which means 65 is my setback for heating, my nighttime setting, if you will. And then on the cooling side, I'm typically setting things for like 74, 75. So my setback for cooling, or my setup, if you will, is typically 80 degrees. If you do it less than that, you're probably not going to save much energy. If you do it more than that, you're probably going to have comfort issues the next morning. So if you don't have any better data for a particular building, go with my number, which is 5 degrees setback. You also need to set it back for a decent amount of hours. Yeah, I guess in theory you could set it back for 1 hour and save some energy, but it's going to be probably immeasurable. The longer I set it back, the better off I'm going to be. The energy savings comes from having a lower differential between indoors and outdoor. The heat that escapes your building or gains in your building, depending on the season, is a function of the temperature differential across the wall. So if I can get your indoor temperature to be closer to the outdoor temperature, the heat and cooling is going to transfer at a slower rate between the wall. That's really what I'm trying to do with a setback thermostat. So if I don't do it for a very long time frame, I don't get a lot of run hours with that reduced temperature differential across the wall. So if you're not doing it for at least 6 hours, you're probably not going to see a substantial savings. Plus, I would say that minimal savings of doing it for shorter hours is really just a training issue. If I have to keep showing someone how to program their stat, and all I'm going to save is a few bucks a year, it's not worth my time to keep showing them the stat. But if they can set it back for 6, 8, 10 hours a day, right, then I can get some decent savings out of it. So those are just kind of my rules of thumb on this based on watching hundreds of buildings as a controls guy. I don't have a good commercial stat, so I'm showing you a residential stat here. But if every single home in the entire country installed a programmable stat and actually programmed it, which is a shock in itself, we would say 5% of all the energy consumption in the entire country. Not 5% of the rooftops, not 5% of the HVAC, not 5% of the building energy, 5% of all of the energy. Planes, trains, automobiles, manufacturing, buildings, houses, everything. Just by doing that in houses. So a lot of energy can be saved by doing this. On average, you're saving about 25% energy from putting a setback thermostat in. Jonathan asks if Ashrae and energy codes established required setback temperatures and differences. And yes, there are some of those. It's different depending on the type of scenario, but there are some rules on what you have to do initially when you set it up. But there's nothing that makes the building occupants keep using those. So I don't really pay attention to that much. Yeah, the guy setting up the system has to plug in these setback temperatures, but there's nothing that makes the building owner use it that way. So that's a good question, Jonathan. Last couple things on thermostats. There's a study from 4 or 5 years ago, DOE. It was mainly a residential study, but the pattern seems to hold true with commercial buildings. When these people were surveyed about their programmable thermostats, 56% of the people did not have a programmable thermostat. 30% did. 14% said they didn't even have a thermostat at all. So either they don't know what a thermostat is, or they have a switch on the wall that bangs their compressor on and off. I don't know which. But of the 30% that had a programmable thermostat, 89% of them were not using it. Right? So that just shows you programmable stats, yeah, they can save energy if somebody's doing something with them. If you're not using it, it's just a waste. Right? So anything we can do to make the programming easier is going to make it better for everybody. Most people have their programmable thermostat in the home button. Anthony asks that 5% savings from that screen, what it was from. It was from residents and didn't have anything to do with rooftop units. It was just from residences only, regardless of system type. But it's the only stat I had. So rooftop units would be a different number, obviously. I just wanted to show you the magnitude of power of programming these things. So programmable thermostats in a commercial environment are extremely easy to retrofit, and even residentially they are, but it's even easier commercially because I tend to have drop ceilings. So if I do have to pull more wires, It's not a big deal. I got a drop ceiling. I could just pop the tile up. Some of the things you want to think about is to get a thermostat with adaptive intelligent recovery. Different manufacturers call that different things, smart recovery, optimal start, stuff like that. What that basically means is if I tell your building to go occupied at 8 o'clock with a normal thermostat, it waits till 8 o'clock, and then it turns on the heating and cooling functions, right? So if you're going to come to the building at 8 o'clock, normally I got to lie to your stat and tell it to go occupied at 7 or 6:30 or 6 or whatever in order for it to get to set point by 8 o'clock. If you have a stat with adaptive intelligent recovery or whatever nickname the manufacturer gives for it, then I tell the stat, go occupied at 8 o'clock. And the stat calculates, based on what's happened the past couple days, how early I need to start in order to get you to set point by 8 o'clock. So if it's been a mild time of year, it'll say, you know what, for the past 2-3 days, it's only taking me 19 minutes to heat your space up. So you know what, I'm just going to go ahead and start at whatever, 7:40, and I know by 8 o'clock you're going to be golden. Right? But if it's taking me, if it's really cold, it's minus 10 this week, you know what, I'm going to have to start an hour and a half early in order to get you to set point by 8 o'clock. So what it allows it to do is flex the start time depending on how cold or how hot it's been outside lately. And that does save you a little bit of energy each day. It's probably only hundreds of dollars a year total, but it's hundreds of dollars a year for doing nothing. For a stat that costs like $5 more. You always want to get a 2-stage thermostat in a commercial environment. I realize people do make 1-stage stats. Those are typically residential stats, which, by the way, don't put residential stats in a commercial building. There's numerous reasons for that, and this is just one of them. I need to have a 2-stage stat, even if it's only 1-stage cooling equipment. Because in order to do the integrated economizer that we're going to talk about in a couple minutes, I have to have 2 stages on my thermostat in order to do that. We'll talk more about that when we talk about economizers. Just know your stat needs to have 2 stages no matter what in a commercial building. You can get thermostats that have a ventilation shutoff output on them. On a normal package rooftop unit with a normal thermostat, programmable or non, when I go into the unoccupied mode at night, and then I get a call for heating or cooling to maintain my 65 or 80 degree setback temperatures we talked about, what do you think the fan does? Well, the fan has to turn on in order to run the heating and cooling, obviously. Well, the ventilation damper is simply tied to the fan. Whenever the fan is on, the ventilation damper goes to minimum ventilation position and brings in 15, 20, 25, 30% outside air, whatever was required by code. There's no reason to do this. You only have to ventilate a building for code if there's people occupied in the building. If there's no people there, you don't have to open the damper. So really, you want the damper to be shut. The building automation guys have done a pretty decent job of this over the years, but if you don't have a building automation system, and you just have a regular thermostat, every single night, every single time there's a heating and cooling call, you're opening up the ventilation damper and bringing fresh air in for people that don't exist. It's the biggest waste of money you can do on a rooftop, and it's so easy to fix. You got to get a thermostat that costs about $20 more than other thermostats, and then you got to run a pair of wires from that thermostat to the economizer of the rooftop. You need a couple more wires to do this. And then whenever the thermostat goes on unoccupied, it tells the economizer damper, hey, you're also unoccupied too. You don't need to open up on these heating and cooling calls. Super easy to do. If you're looking for specific thermostats that do it, we created a list of them and put them on the FAQ section for the Focus on Energy Wisconsin rebate program. So there's a bunch of them listed on there, and I got it set up so you can see the model number of the thermostat, you can see the terminals you got to wire to, and the settings you got to change on the stat to make it happen. If you can't find that list on their website, you want me just to send it to you, that is fine. Also, I can do that. You can make these thermostats internet accessible, right? Put them on Wi-Fi or whatever, and that is great. And I get questions all the time, well, how much energy am I going to save by doing that? My answer always is the same amount of energy as a regular programmable stat. The Wi-Fi stats don't do anything extra. The one thing I will say, though, is that if your regular programmable stat was not programmed because you didn't like programming it, and you like messing with the app on your phone to program the Wi-Fi one, so now you actually use the program, well, now you are going to save energy because you're actually using the thing the way it was supposed to be used. So you could save some energy that way. In general, for programmable thermostats in a commercial building, for 5 tons and up, the payback is usually rapid, less than 6 months. The bigger the rooftop, the faster the payback even. Like I said, you can hook these things up to the web. We used to have to run it on Ethernet. Now we just do it on Wi-Fi, which makes it super easy, and almost all buildings have Wi-Fi. You're going to get really basic stuff. It's not going to be full building automation type stuff, but you're going to get what you need. What are my current temperatures? What are my current set points? How many stages of heating and cooling are running? Do I have any alarms like low temp, high temps, etc., etc.? Right? But it's very useful. This is an old stat. This is one of the first ones I did back in, this one was 2006. We started doing these in 2005. I'm not even sure if this manufacturer's in business anymore because now everybody has these stats. But it looks like an old school screen. The new ones look much sexier, but it's the same thing. It looks like a ton of data because it is, but this is normally what people are programming on their stat one screen at a time. 43 screens later, they might have their stat programmed, maybe. With these things, at least you can see the whole schedule at once and see what you want to change and tweak and optimize. Right? That's the whole goal with these guys. Like I said, now there's apps and everything to make it even easier for you with all the different manufacturers. Everybody's got at least 2 models of Wi-Fi stat, if not 15. So it's really easy to do this kind of stuff now. And then to make it even easier for folks, there's generally free money involved. Most of the Midwestern utilities, most, not all, but most of them have some kind of rebate. Sometimes you can double dip and get a rebate, like in Indiana. You can get a rebate from your gas and your electric utility. So you get $90 back on your programmable stat. It probably doesn't even cost $90, and if it does, it's barely more than that. So you can get quite a bit of money by doing that. Wisconsin's actually kind of nice. They actually separate it from standard programmable thermostat, $40, to advanced programmable, $100, which means you got to do the extra things I just talked about. You got to interlock to the ventilation damper to shut it at night, and you got to have the ability to do 2-stage integrated economizer, right? But then you get more money. All right, so that is thermostat discussion. If anybody has any questions, they can go ahead and type them in. I'm going to launch another poll question here. All right, which mode generally has the most annual run hours on a rooftop unit? All right, is it the heating mode, the straight-up compressor-only mode, the ventilation mode, the economizer only mode, or the integrated economizer with the compressor and economizer running together? So like about 76% of the people voted. I'm going to give it another 10 seconds. And I'll shut it in 5, 4, 3. All right, we popped the results up there for you. 91% of the people said ventilation only mode, which is correct. That means I'm neither heating nor cooling. I'm just bringing in fresh air for code. That's the vast majority of my run hours. Right? That was that on that chart, color chart. That was the middle blocks of all those guys, where it was well more than half the hours in that scenario. So you guys did a good job on that one. I got most of them right. All right. Let's talk about economizers a little bit. All right, so outdoor air economizers. This is the way to free cool your building, if you will. Right? So at your house, if it's whatever, it's Thanksgiving, you got a bunch of people over, it's 50 degrees outside, but you're hot, you probably don't turn your air conditioner on. You probably just go around and open up a bunch of windows and you're fine, right? Well, in commercial buildings, generally speaking, we don't have operable windows. And when we do, people open them at the wrong times anyway. But we don't typically have the operable windows. So what we do on a rooftop unit is you put a window in the rooftop unit. If you want to open up your window and get free cooling on a cool day outside, but I need cooling inside, we open up the window in the rooftop unit. We call that an economizer. Sometimes it's called a free cooling damper. Right? The goal is to shut the compressors off and run the economizer damper open to bring free cooling in for people. There are 3 main ways that we control an economizer. There's other ways, but these are the ones that are 99.99% of the time used. And of those 3, the dry bulb temperature is by far the most common. So what that means is I take a particular temperature outside, and almost all technicians set it at 55 degrees. Ask the guys in your shop or on the next job you go to, what do you set the economizer for? And almost everyone will say 55. If you ask them why, they'll say because that's what they were told to do 17 years ago when they were hired. Nobody knows why. 55 degrees is a safe number. Nobody gets a complaint call. I've been using 60 degrees for at least the past 10, maybe 12 years, and I've had no callback issues at all because of that. And like I said, I was setting up economizers as a controls contractor, and I set them all for 60 and no issue whatsoever. And I'll show you some charts there explaining why 55 and 60 numbers evolve. But dry bulb means, in my example, if it's below 60 degrees and you ask for cooling in the space, meaning the thermostat calls for cooling, I will open up the damper and give you cooling from outside instead of turning the compressor on. I can't get much more than 60 because I risk it being humid outside, and now things aren't going to be so comfy when I start sucking that air in. So my counter to that is, well, instead of looking at dry bulb temperature, why don't you look at the humidity outside? So what we really do is we look at the enthalpy, which as most of you guys know is both the sensible and late heat content of the air, right? So for the simple people like me, that basically means look at temperature and look at humidity. So then I can get much more aggressive with my temperature. Instead of taking air below 60 degrees from outside and using it for cooling, I can say maybe take 70 degree air and try to cool your building with that, as long as the humidity is low. I don't want 70 and humid. I want 70 and low, or 65 and low. I don't want high humidity air coming in. So I look at both and make sure I don't take that air. Can I cool your building with 70 degree air? Probably not, but it's better than the 75 or 78 or 80 degree return air that I have to pick from. I can only get air from two places, right? The outdoor air or the return air duct. Well, if the return air duct is 75, 76, 77, 78, I'd rather have the 70 degree air. I'll have to use my compressor also, but it won't have to work as much. And then the third type is differential enthalpy. That takes what I just said on enthalpy and guessing and says, well, let's just measure it. Let's measure the outdoor air enthalpy, and let's measure the return air enthalpy. So measure the temperature and humidity of both air streams. And whichever one is cooler and drier, just use that one, right? So I don't care if the enthalpy is only, a few points lower on the outdoor air than the return air. If it's lower, I'm going to take it, right? So who's a little bit cooler and who's a little bit drier, give me that air. The compressor will make up the difference. Dry bulb economizers are most commonly used. The issue with enthalpy economizers, one, technicians are a little scared of them sometimes, and we do economizer classes for techs to help them out with that, both at our office and at the union to make it easier. The other side of the equation is enthalpy sensors historically drift out of calibration, and it kind of becomes a pain in the butt. So I've kind of got a rule of thumb that I've been using for several years now. If the rooftop unit, and I'm going to save more energy by doing the enthalpy economizer instead of the dry bulb, let me just say that. So if the unit is bigger, and in my mind bigger means 15 tons and larger, it is worth it for me, even if I have to replace the enthalpy sensor every 5 years, not even calibrate, but just replace it every 5 years. It is worth it for me to do that on the 15-ton unit and buy a new sensor every 5 years, because the energy savings is going to more than make up for that, right? But if I got a 3-ton rooftop unit, it's probably not going to make a lot of sense. The savings won't be that much more because the energy costs aren't that much to begin with, so buying a new $200, $300, $400 sensor every few years is not going to be a great scenario for me, right? So above 15 tons, definitely go enthalpy. Below, I'm going to say 6 tons, go dry bulb. And in between, we can argue about in between depending on how big or how many hours the system is going to be running, right? And who's going to be maintaining it. A couple other things to think about. An integrated economizer, what that means is, let's suppose I take air that's warmer than 55 degree air, right? It means I probably can't cool the building with it all on its own, so I might need some help from the compressor. An integrated economizer means I use the compressor in conjunction with the economizer. I use both. In order to do that, I have to have a 2-stage stat, even if I have a 1-stage compression cycle. All right, so run the two together is called an integrated economizer. I also have to think about pressure in the building. If I'm going to open this damper and suck a lot more outside air in, where is that air going to go? Whatever I suck into a building has to have a way to get out of the building, right? No choice at that. It's got to, whatever goes in has to come out. So if I bring more air in through the economizer, I have to have a pathway for it to get out. On small rooftop systems, we typically use a barometric relief damper, which is nothing more than a piece of sheet metal, a little counterweight action to it, and I got to build up the pressure in the building to push the sheet metal open and relieve the air. On bigger systems, I'm going to want to have a fan-assisted type thing, either a power exhaust in the rooftop to suck the air out when the damper's open more, or separate exhaust fans unrelated to the rooftop running on building pressure sensors. I definitely want to get a thermostat that has that occupancy contact that I mentioned a few minutes ago, and then wire that occupancy contact to the economizer on the rooftop, the economizer controller. All the modern economizer controllers have an input waiting for that, right? So if I get the right thermostat that has the output, and I have an economizer that has the input, I just need to get the wires from point A to point B, and I can make that happen. And then whenever the unit goes unoccupied at night, we also shut off the ventilation portion, right? Because this damper is doing double duty. He's doing ventilation, and he's doing the economizer function. Ryan writes in a question, how is the power exhaust fan controlled building pressure? Right, there's two ways you can control the power exhaust. The simple way, right, is to have, typically we'll put a pair of, so let's say you have 2 stages of power exhaust, just for argument's sake. I'll put 2 switches on the outside air damper, and let's say that when I get to, I'll make up some numbers right now. When I get to 35% open on the damper, I'll turn on the first stage of power exhaust. And then when I get to, let's say, 70% open on the outside air damper, I'll turn on the second stage of exhaust. That's the simple way to do it and a very common way to do it. Building pressure is a better way to do it. It just costs more money, right? So it's kind of not always used. Building pressure means that I would want to have a variable speed exhaust fan, and I would measure the pressure in the building. And for most building types, I'd try to maintain some slightly positive pressure, right? So a little bit of air leaks out of the building instead of a little bit of air leaking in, right? The better of the two evils. And I'll typically try to maintain between 0.03 and 0.08 inches of water column, and I'll ramp up my modulating exhaust fan based on that. But if I just have a 1 or 2 stage fan, then I'm going to go with the switch idea. When I get to a certain position on the damper, switch kicks on and turns on one of the stages of power exhaust. Right? So if you can get the building pressure sensors going and you got a unit that's large enough to have a VFD option for the power exhaust, that's great. All right, so continuing on. Paybacks on economizers are generally very quick. The bigger the unit, the faster the payback. The smaller the unit, the longer the payback. On average, they're typically less than 6 months. Especially if you're buying them on the rooftop unit. If you're retrofitting them, then it might be a little bit longer because you got a little bit more labor you might not have otherwise have had on there. That's just kind of showing you an example on this hood over here on the right-hand side. This top pathway here, that's the outside air coming in, and down here is the exhaust air, in this case 2 fans blowing out. Depending on where you're at, you may have to add a little bit of ducting to this outside air intake because there might be certain rules about distances between the intake portion and the exhaust portion, even though it's not hazardous exhaust, it's general building air, but sometimes they have rules like that in different towns. But I got to have a pathway for the air to get out. From a code standpoint, economizers are frequently required, right? So this is what's going on with the current codes. This is the IECC 2012, which based on the map I showed you earlier, there's already 20 plus states that are on that particular code or higher. For those climate zones down there, which is pretty much all climate zones except the 1 climate zones. And by the way, the only place you're going to see the ones is Miami. If you live in Miami, you can cover your ears. Everybody else got to do economizers if you're on the current code. Right? If you're on 2012, anytime you're more than 33,000 BTUs. What's 33,000 BTUs? It's like a little more than 2.5 tons of cooling. Rooftop units, for the most part, start at 3 tons and up. So pretty much every single rooftop unit has to have an economizer by code in more than or almost half of the states already. And certainly most of the ones that we're working with. And I'll show you the other states in the area in a second. So just remember, for 2012 code, which all the states in this area are either on or will be on shortly, you need to have an economizer above 33,000 BTUs of cooling. That's a key number. All right? And I'm not going to read all the economizer code language to you. There's some exceptions to that, but for the most part, a normal building, like an office or a school or whatever, it does not meet the exceptions. So for most of the time, we got to do it. Right? If you got a water side economizer because it's a big hydronic job, then that could be your way of getting the economizer. It doesn't have to be air side. This is the climate zone map. We're going to use this several times throughout the different topics today and next week. Right? But where I'm standing at right here in the Illinois area, I'm in climate zone 5, which is green. And I am to the right half of the country, which is the moist half. So I am 5A, right? If I go back one over there in the table over there, 5A, that includes me, right? In fact, everything in A, B, and C, everything except for 1A and 1B has to do it. 1A is Miami down here. 1B is not even on this map anywhere, right? It doesn't even apply to us in the United States here, right? Actually, it might be Hawaii. I don't know. If you do a job in Hawaii, God bless you. For right now, everyone other than Miami has to do this. And you can see as you go up, if you're in Wisconsin, you're either 6A or 7A if you're in purple in the northern half of Wisconsin, right? And then if you're in Minnesota, you're either 6A, 7A, or 8, right? It just depends on how far up northern you go. But for economizer rules, everybody's got to do it. The reason there's so many categories is because this same map gets used for lots of different things, not just economizers. Bruce types in, I don't know if it's a question or a comment, heavy snow can cause problems in the winter. I'm assuming he's talking about economizers. And it is possible to entrain moisture into an economizer. One of the ways we help do that, if you go back to this screen here, you'll notice that mesh grid on the economizer. That's to help prevent moisture and things like that from getting as easily sucked in, right? So if you're doing a built-up system like an air handler, you should still do something like that in order to prevent that problem from happening very frequently. And then Jonathan writes a question in, energy codes typically have a high limit temperature shutoff temperature, but does this typically mean that you must economize up to this temp, or would 60 degrees be acceptable? I'm going to look into that question, Jonathan. I believe that means you cannot use economizer above that temperature, but I don't think it means you have to use economizer below that. And certainly if you go with an enthalpy economizer, then the rules would be different. But I will get the answer to that, and I'll put it up on the screen next week for all of you guys, so you can see that answer to that specific question. All right, if you are in states that have 2009 energy code, which is basically 18 states at this point, which is most of the Midwestern states, including Michigan, for you folks that are on there, then the number is 54,000 BTUs. So that was the old rule in Illinois. Now we're on the new 33,000 BTU rule, right? And more climate zones get affected than the old rule used to, right? So that's the rule there. If you're in Wisconsin, you're on the 2009 code, but there's a special amendment in Wisconsin to that code specifically for packaged rooftops and says, yeah, we're going to do the 54,000 for most systems, but on a packaged rooftop, we're going to do the 33,000 number, right? So if you're on the 2012 code or 2009 in Wisconsin, 33,000 is your number. If you're in Indiana, well, then you're just, you're still behind the times, if you will. For our climate zone 5A, 135,000 BTUs, so it's like a 12 or 13 ton rooftop. You would have to do an economizer or larger. And for folks in Minnesota, if you're in the northern half of Minnesota, you don't have to do it at all yet. If you're in the lower half of Minnesota, then you are like Indiana, 135,000 BTUs, although like I mentioned, Minnesota is switching to the new code. So in the next few months, Minnesota is going to go from 135 down to 33,000 BTUs for the whole entire state. So it's a big change for those guys. All right, so a few more things with economizers. You got to test economizers. It should be on anyone's rooftop maintenance schedule. Typically, I tell folks you got to test them at least twice a year. Once going into the cooling season, once going into the heating season. Because if it's not working, I might bring in too much or too little air. And either way, it's going to cause me an energy problem. Sensors, temperature sensors are usually really, really good. They're typically thermistors. Thermistors tend to not drift. They tend to be reasonably accurate, plus or minus a degree. And for what we're talking about here, horseshoes and hand grenades, 1 degree is totally fine. They tend to not drift, so you're fine there, and typically do not need calibration, but you still should check them. The enthalpy sensors are notorious for drifting out of calibration, as are CO2 sensors, although there's a fix on the CO2 side, which I'll talk about in a little while. But the enthalpy sensors are the ones you got to pay attention to. I'm not saying don't use enthalpy sensors. I'm just saying you need to plan on every 3, 4, 5 years of calibrating them and or replacing them. That's why I say on bigger rooftops it makes a lot of sense. On smaller rooftops, maybe not so much. And then the big thing is people set them for the wrong temperature set points, or they lock the dampers open or closed. Things like that are big issues. I'm going to skip the OA calculation and go on to the economizer itself. These are typical economizers you will see in rooftops. Almost all of them are Honeywell. They dominate the market with 90% plus market share of rooftop economizers. So I'm not a Honeywell guy or anything. It's just that that's what's in the units. This is a typical Honeywell economizer that you'll see in a lot of units. I just pointed out so that way when you see it, just so you know, you cannot add demand control ventilation to this particular economizer. It's not capable of it. It can do the dry bulb and enthalpy and differential enthalpy and all that stuff, but it's too old to do DCV. The good news is you're not seeing many of these in the field anymore because they were obsoleted years ago, but you still run into them every once in a while. This is an extremely common actuator, or economizer controller that you will see in rooftop units. This one says carrier on the side because Honeywell makes it for them, but Honeywell makes it for almost everybody, right? It's a 7200 series controller, and it can do DCV, and you can even see on there, depending on how good your vision is, some DCV setting potentiometers on there. So you know it does do DCV. So you can do upgrades with this particular one in the field if it's already out there. And that's just a drawing view of that. I will also point out in the bottom of that controller there, you see the ABCD switch. Just keep that in mind, and we'll talk about that a little bit here. All of the Honeywell economizer models are being obsoleted, and there's only going to be one going forward, and it's the W7220, which is the one you see on the top there with the display on it and the green and red and everything. That replaces all the other models that they have. There's numerous reasons for that, some of which involve the staged air volume fans, which we'll talk about next week, and why we have to have that economizer controller to do the staged fans. But it's basically the replacement for everything, and it is capable of doing everything we talked about plus the DCV. We're not going to use this today, but in the service tech classes, we do use this simulator. This is one Honeywell has for their economizer controller. There's also one for the new 7220, which, by the way, that 7220 is referred to as the JADE, J-A-D-E economizer. So there are little applets guys can put on their computer, or we can use in our classes, that we can simulate all these different scenarios, and they can see when things turn on, when they turn off, when they open, when they modulate, and we can play with the values as opposed to messing up somebody's real system. So those are available. They're free tools you can use. I'm hoping everybody is familiar with psychometric charts. If not, come to the webinars in May. We're going to talk about them a little bit in that webinar. But for the quickie version of it, basically on the bottom of this chart is all your outdoor air temperatures, from lower to higher, going from left to right. And the vertical axis is all your moisture content, going higher from bottom to top. And then you got these curves all the way throughout the chart that are your relative humidity curves, right? So 25, 30, 40, 50%, etc. So the way I'm looking at this here, the yellow line is the 60-degree temperature line. Everything to the left of that is below 60. Everything on the chart to the right of that is above 60. If I'm below 60, you should be in economizer mode. I know a lot of technicians set it for 55. I'm doing my chart here at 60 because I'm telling you 55 is too conservative. If you go with 60, I personally promise you, you're not going to have a problem job, right? And then if we move on, and then the right, the red line, is everything that would require mechanical compression. If I do the enthalpy, then I get this angled yellow line, right? I'm looking at temperature and moisture content to decide which air is better, right? So if I say anything, in this example, anything below 65 and dry, then I can kind of deal with that. And that basically gives me this extra, what I'm circling here in red or whatever that color is. That's those extra run hours that I didn't have when I have a straight line here at 55, right? I can't claim those extra hours. Enthalpy-wise, I'm pretty good down here, but it's just going to be too warm for me to work with that air. So economizer over here that I otherwise wouldn't have had, and then a mechanical compression on this side over here. Integrated economizer means I run the compressor with the economizer. So the blue line to the left of 55 means I'm doing economizer only. The red line to the right of whatever that is, 75 degrees, I'm in compression only mode. And when I'm between 55 and 75, I am in the hybrid mode where I have both economizer and compressor running together, although less stages of compression typically. I don't need to do as much work there. And those numbers change, and they're not really based on an absolute temperature. They're based on the thermostat calling for second stage of cooling, right? So these numbers are just kind of like theoretical guesstimates, for averages. But in the real world, when the compressor kicks on is when the second stage of the stat says, hey, I need cooling. All right, so the way it works is your thermostat, the Y1 on your thermostat, which is the first stage of cooling, he tells the economizer controller, hey man, I need cooling. Then the economizer controller looks at his outdoor temperature sensor or his outdoor enthalpy sensor and says, is the outdoor air suitable for me to give you free cooling? If the answer is yes, he modulates his damper open to maintain a specific mixed air temperature, typically 53 to 55 degrees is his goal. If the thermostat in the space still does not get satisfied and the temperature continues to rise inside the space, then the second stage of thermostat calls. And that second stage wires to the economizer controller also. The economizer says, great, and he ramps his damper open, and he's, well, I'm already giving as much free cooling as I can. If it's not good enough, then I'm going to go ahead and allow the compressor first stage to turn on. All right. If the thermostat calls for cooling and the economizer controller gets that signal, and he says, you know what, yeah, I know you asked for cooling. It's not really a nice day outside. It's like 92 and nasty, so I'm just going to not open the damper, and I'm going to go right to the compressor right now on stage 1. Right, that's basically how that guy works. We look at those ABCD curves on the economizer controllers. Those represent the enthalpy settings, and these are what those curves look like. There's a little hard shut-off at the high humidity point, but then after that, it's actually a curve, right? When I do these classes face-to-face, I always ask everybody, well, what curve do you think technicians set it for? Almost all the time in the field, I see this set on D, which is like a super conservative number that they know they'll never get a single callback on no matter what. All right? In most cases, you could probably set it on A, and you probably would be fine, because that lines up pretty well with the chart that I just showed you a few minutes back. Right? Oops. Right? That yellow line right there, it's kind of similar to that A line, right? So I could probably set it on A. If you're a little bit nervous about that, set it on B. What I tell the technicians in class, I tell all of them 100% of the time, just set it on B, and you're not going to have a problem. C and D don't save enough energy. A, you're kind of right at that threshold of, well, is it too high humidity or not? B is a safe number for everybody, right? So as a rule of thumb, set it at B on that enthalpy curve. Economizers are typically rebatable in most areas around here. If you're in Illinois under ComEd, it's $50 a ton. Wisconsin is not a ton number; it's a per unit number of $250. But you can see there's different ones that are out there. You do want to read the rules on that because sometimes there's additional rules. If you're a certain size unit, you can't get the rebate because code might require you in certain cases anyway, et cetera, et cetera. If it's a new unit versus a retrofit unit, that makes a difference when the codes kick in or when the rebates kick in and not. So just kind of pay attention to the rules before you promise it to somebody. Dave types in a question. Does the discharge economizer sensor drive the damper wide open when the compressor and outdoor damper run together? Okay, so the position of the economizer damper, once we ask for economizer cooling, then after that the damper modulates solely to maintain the temperature that's typically installed in the mixed air temperature cabinet. Sometimes guys do put it in the discharge position, but typically it's in the mixed air position, and you can tell the economizer controllers which one you installed it in. But he's trying to maintain that specific temperature. So I mount it in the mixed air. I'm trying to maintain typically 53-degree discharge air, and I'll keep modulating my damper open until I get 53-degree air. And then the compressor gets kicked on based on the thermostat calling for it. So hopefully that answers his question. Dan asks if it is DCV or DVC. It's DCV, Demand Controlled Ventilation, DCV, which we're going to talk about next. Try to get this topic, I don't know if I'll get the whole thing in, but we'll get part of it in today, and then we'll probably finish it up on Monday and then move into the staged fan discussions. All right, so ventilation control. And this is kind of a mini version of DCV. This is normally like an hour-and-a-half topic, but we're going to try to make it a 20-minute topic. So we control ventilation the same way we always do. We look at some book, some table. It says bring in this much outside air for this many people or this many square feet. Lock it in, leave it there forever, never touch it. That's typically what the codes historically have asked us to do. That is a timeline of what the codes have looked like. You can ignore that giant pyramid on there because that was very few locations, and those buildings are so old, pre-World War II, that those buildings have certainly, hopefully, been retrofitted since then, right? But the bulk of the buildings that you are working on and retrofitting now are probably built in the 1980s and 90s, right? So they're probably built on either 10 CFM per person, 5 CFM per person, or 15 CFM per person, right? That's what all the Ashrae standards and hence all the codes typically did. We dropped down to the 5 for a little while there as a reaction to the energy crisis of the 70s. We immediately got away from that and went back up to 15 because that 5 was too little and caused some indoor air quality problems in buildings, some sick building syndrome issues got blamed on that kind of thing, et cetera, right? So we went from 10 down to 5 to 15. Then for a brief while, for 5 years, we went up to 20, which is really high. And now I'm going to say we're at about 17. I say about 17 because things are a little different from 2004 and later. The way the Ashrae Standard works is there's no longer a CFM per person. Now it's a CFM per person plus a CFM per square footage, and you add those two numbers together. So I say about 17 based on an office building of a average density, right? If I have a more or less densely occupied building, that number will be different. And I mention office buildings because that's just a high volume of projects. So the way the current standards and codes are for office buildings are you need 5 CFM per person, and you need 0.06 CFM per square foot. You add those two numbers together to find out what your code ventilation area is. There is basically one reason why these numbers are separated instead of having a bulk number, and we got the CFM per person and CFM per square foot. The person is basically to dilute down building occupants, right? People smell and have body odors and all colds and all that stuff. The square footage portion is basically to dilute down building pollutants like VOCs off the carpeting and paints and furnishings and all that stuff, right? That's why we have the two numbers. And the major reason of separating these two is because before we did that, it was very hard to do demand-controlled ventilation systems because I can modulate for the people portion, which you're going to see here in a minute, but I didn't really have any way of knowing what the building portion was. Now I do, right? So for argument's sake, let's say I have a building, we'll make the numbers easy, an office building with 100 people in the space. So I need 500 CFM of fresh air coming in whenever that building's occupied for the people portion. And then let's just say that I have 10,000 square feet, right? So then I need 600 CFM for the building portion. So in total, for code purposes, I need 1,100 CFM of fresh air to come in the building whenever the building is occupied, right? Meaning that I'm in normal building operating hours, 7 a.m. to 7 p.m. or whatever the building's set for. What DCV allows me to do is it allows me to modulate, in this case, this 500 number. I can go anywhere from 0 to 500 on the people portion. The 600 number I can't touch because that's not related to people or CO2, as you're going to see here in a minute. But I can modulate the people portion, right? So that's kind of how that's going to work. And then, as a point of clarification, all building types have a different number. The 5 CFM per person and the 0.06 CFM per square foot, that is for an office building. If I went and did a daycare, it's like, I forget what it is, I think it's like 15 CFM per person and like 0.18 CFM per square foot. And if I did a school, it'd be something different than that even. And if I did a manufacturing plant, it's different for that. Right? There's all these different rules for different size scenarios. I'm going to pop up another poll question here. All right, the question is, for most states, RTU economizers are required above what cooling size? And I'm going to say for most states, meaning the International 2012 code, because that is 20-some states, which is by far more than any other code being used. So basically, what's a 2012 code require an economizer for? 24,000 BTUs, 33,000 BTUs, 36,000 BTUs, 54,000 BTUs, or 5 tons, right? So most states means International Code 2012, which encompasses 20-plus states. This one could be a little tricky. I try to make most of the questions fairly easy, but a couple of them require people paying attention, although most people are getting it right here. 85% of the people voted, so I'll give it another 10 seconds. I'll close it in 5, 4. All right, 83% of the people got the answer correct, which is 33,000 BTUs is one is required to have an economizer. We'll do another poll question here just because, what the hell. This one should be super easy, and it's somewhat subjective, but you can kind of tell the theme here. True or false, rooftop units cannot be energy efficient and remain the lowest cost first choice. So this is more of an opinion-based one, but I think you probably can guess. You already know that rooftops are the lowest first choice, so can they stay that way and be efficient? While you guys are doing that, I'll clarify Tony's question. Tony's asking for DCV, and when I said modulating the people portion of the code during the occupied mode, what about unoccupied? Can I go to 0%? Yes, you can go to 0%, absolute 0%. When it's unoccupied, you can modulate the people portion down to 0, and the square footage portion goes down to 0. Both of them 0. The other Anthony, I see your question there, and I will take care of that separately. Anthony Morgani, I'll take care of that question separately. Or maybe send me an email to remind me to do that for you. Okay? All right. Almost everybody got this correct, which is false. It is possible to make rooftops efficient and still have them be the lowest first cost choice. That's basically the whole entire purpose of the webinar here. Oops, sorry, hide that. All right, let's go a little bit further in here. We're probably end somewhere in the middle of DCV, but that's okay. So for a building that was designed on the 20 CFM per person code, which a lot of them were in the late 80s, early 90s, should be mid-90s, 25 people for the building would have required me to bring in 500 CFM. If you did out a building on the new code, that's fine, no big deal. You can still just do a pretend example in your head that equated to 500 CFM, certain square footage, certain number of people, etc. A normal building, what I would have done when less people are there, there's only 5 people there instead of 25, I still would have gave you 500 CFM of code air. And then when there's one lady counting the money all by herself, she probably shouldn't be at the bank by herself, but if she was, she still would get the 500 CFM, right? So the idea is that you're always getting the same amount of air no matter what on a traditionally designed building. I want to figure out how many people are there in order to figure out what I want to do with this. So there's things involved here, like the Ashrae Standard 62.1, which is the ventilation standard for the country. The mechanical codes, such as the International Mechanical Code, piggyback off that standard and literally cut and paste the ventilation tables into their document, just like the energy code people, IECC, do with Ashrae 90.1. Ashrae is kind of the research backbone, if you will, and the code people take the Ashrae stuff and write it in code stringent language. A couple things to point out when we talk about these CO2 sensors. CO2 sensors are a measure of the ventilation rate. It tells you how much CFM you're bringing in per person. It has absolutely nothing to do, directly speaking, with indoor air quality. Sure, if I bring in more fresh air, I will dilute down pollutants and probably make your air quality better, but it's not a way to measure indoor air quality. CO2 does not tell you the air quality is good. You could have tons of pollutants going on in the building, and CO2 doesn't have anything to do with those pollutants, right? So you can have a bad building, and CO2 is not going to tell you that. CO2 just tells you how many people are in the space and breathing oxygen. That's literally all it does for you. Typical ranges that I'm trying to get to, typically 1,000, 1,100 parts per million is a typical normal goal to have CO2 in the building. If I have lower levels of CO2, I'm generally overventilating. If I have higher levels of CO2, I'm generally underventilating. Sensors can generally cover radius about 20, 25 feet, right, which takes care of most spaces. They should be mounted about 5 feet above the floor. We generally frown upon putting them in the return duct. There are several reasons why, which we'll talk about probably on Monday, the beginning of Monday. But generally mounting them in the space at the breathing zone level, 3 to 6 feet off the ground, is what we need to do. Some standards, like the LEED standard, for example, prohibits you from putting them in the return duct. You have to put them on the wall. Putting in the return duct ends up giving you an average diluted answer instead of giving you a factual answer. Actually, speaking of that, Jonathan writes in, is DCV typically controlled by average return air CO2 for multi-zone systems? Definitely not. You cannot do it that way for sure. If you have a zoning system, you absolutely cannot put the sensor in the return duct. Think about it this way. If I got 10 offices and a conference room, and each office has one person, I got 10 people. I got a certain amount of ventilation air I bring in for that space. When all 10 people walk out of their office and walk into the conference room together and breathe in there instead, has my CO2 level at the return air duct changed at all? No, it has not. It's still 10 people breathing on that system. But now I need to get more fresh air into the conference room instead of getting it into the perimeter zones, right? So I cannot put the return air sensor in the, put the CO2 sensor in the return duct on zoned systems. Absolutely cannot do that. You need to put it on each individual zone, or there's a loophole for equation 6.1, which we'll talk about. So CO2 is not a contaminant. It is found naturally. People exhale it. It is not harmful to people unless you get to insanely high numbers of 30,000 parts per million, and you can't get it that high. Literally, unless you put your head inside a sandwich bag, you can't do it. I have sensors sitting here on my desk. I breathe on them all the time. It's very hard to get them into the 5,000 range, let alone 30,000. This should be obvious, but CO2 and CO are not the same thing whatsoever. CO is carbon monoxide, a product of incomplete combustion, and is harmful, poisonous gas. CO2 is carbon dioxide, is just a natural product of people exhaling oxygen, or inhaling oxygen and then exhaling. People exhale at very predictable rates. It's a very measurable thing. So if I know how many people are in a space, I know how much CO2 they're producing. I'm going to leave this as the last slide for today, and then we're going to pick off from this point. CO2 ventilation rates are a function of what you're doing, right? So the more active you are, the more you are breathing, hence the more you are exhaling. So most of our check figures and rules of thumb come from classrooms and office buildings where people are seated and relatively calm, although a classroom might not be calm. But if you're doing a different job, where people are at a fitness center running on a treadmill or something, then the rules might be a little bit different. Just keep that in mind. The more active I am, the more I'm going to suck oxygen in, hence the more CO2 that I'm going to produce. It just changes some of my math on my controls. It doesn't mean I can't do the system. All right? All right, so we're going to cap things off there since it is 1:30. And we're going to leave things off there. I'm going to go ahead and end the recording. I'll post the recording for anybody who wants to view it this week. And then on Monday, next week at noon, we'll pick up where we left off. If you have questions in the meantime, email them to me or something like that, and I will be happy to try to answer them for you.